rolling.
Good.
Oh, okay.
Oh, redox. Oh gosh.
What?
I don't like redox
Thank
reactions.
God. This is so much better.
Forgot how to do all of it.
I'm just kind of, I'm mostly just kind of tired of acids. Kind of tired of thinking about acids.
Yeah.
But, alright, we're here.
This is thinking
He's the
about
guy who
water.
drops the base.
Still, kind of, I mean, I guess.
Wait, do you remember the picture of the lion at Citric County Zoo I sent?
Yeah.
you? This is Leo.
There goes.
Okay,
There's
so
also oil spill.
yeah, I know you've all been introduced to redox reactions, okay? So basically, today we're gonna cover everything you already know and then add to it. So, first off, get out that periodic table,
What was that, Jason?
okay? It's this yellow sheet.
That's coming.
And on the back side of said yellow sheet is a reduction table, okay? This
Ooh.
is going to become your main reference going forward. So, because you can glean a tremendous amount of information from a reduction table if you know how to use it. So we're going to get into it. So, there's various forms of this. I always remember Leo says Gur because I was like fondness for Africa and lions, so this is what I've got, Leo says Gur. So, it basically boils down to a tug of war for electrons, okay? And Mother Nature is only going to allow a reaction to happen if Mother Nature gains something from it, which in this case is going to be a lower energy state. So that's your guiding light. There's two things that happen in a redox reaction. You have a loss and gain of electrons. Both of those have to happen. We don't have reactions and we don't have ox reactions, okay? We have redox reactions. Something gets reduced, something gets oxidized. So basically, whatever is going to gain the electron has a stronger pull for the electrons than what already has the electrons, okay? So it's just a tug of war. So what I'm going to do is something simple, and y'all have seen this done before. So I've got, where did I put it? This test tube, which I've filled with 1 molar hydrochloric acid. So on an atomic level, I got a bunch of hydronium ions, and a bunch of chloride ions, and I've got a bunch of water molecules. And then I'm going to jump into that a chunk of magnesium, okay? So I'm going to drop this in, okay? And right away we get a pretty vigorous reaction taking place, get lots of bubbles, okay? And we're going to collect that gas for a while. So let's have a quick refresher. I've got magnesium, and we're going to write out the Chem 1 version of this in hydrochloric acid. So here's the kicker. This is why you have to be able to look at this thing in terms of charge. So remember, if something is in an elemental form, what's the oxidation state of anything that's in the elemental form?
0.
0. So here you have a chunk of magnesium that's at 0. So the hydrogen clearly is at 1 plus, and the chlorine is going to be at 1 minus. So here's what basically happens on an atomic level. The hydronium ion, otherwise known as a proton, runs up to the magnesium and says, yo, sup, give me an electron, okay? So the magnesium clearly says, hey, we're cool, right? I don't want any problem. Not only am I going to give you 1 electron, I'm going to give you 2 electrons, because it's got 2 electrons out there in that outer valence shell a long way from the nucleus. So it's like, if you look at magnesium, there's 12 parents, and they're at the zoo with 12 electrons, okay? The lions come up and says, hey, we need a couple of, kids in kind of in payment. Okay, here you go. Take the 2 outer shell kids, right? Timmy and Tommy, sorry, you're gone. The lions are not happy because the lions are like the protons, okay? So everybody wins. But now you have the 12 parents pulling in the 10 kids. They're going to probably pull them in a little bit tighter. So a magnesium ion is actually smaller than a magnesium atom because you've lost that outer shell electrons and you're going to hold the kids in a little bit tighter. So we got this going on, right? And we're generating this hydrogen gas. So Vin, can you hold that tube for just a second? So one of the things that we can check if we're producing hydrogen gas is that we should be able to make the test tube pop.
Hey, you got a new lighter.
I did. This one sucked. Okay? So here we go.
Aww.
It never gets old. Okay, so we made the test tube pop, right? So there was actually two different redox reactions taking place. The first one generated hydrogen gas. So out of this reaction, the magnesium was sitting here. You had the hydronium chloride, you get magnesium chloride and hydrogen gas. So now, in the Chem 1 version of this, we balance this and we go, oh, this is cool, great, we did chemistry, right? Oh, look at us, okay? And we have hydrogen gas because that's one of the diatomics and all this good stuff. So this is the Chem 1 version of this, okay? And it's cool, but it really doesn't, it actually gives us too much information. Mainly because the chloride ions are there in the solution, okay? Chloride ions are here. And after I get done, the chloride ions are still there because this is soluble, okay? How do I know that magnesium chloride is soluble? If it was insoluble, what would you see?
Precipitate.
You'd see a precipitate, okay? I don't see a precipitate, okay? If I did, then that would look completely differently. So I'd begin to see this formation of a precipitate at the bottom of the test tube, which I don't, okay? So this reaction is just humming along, right? We're still generating all of this hydrogen gas, and it feels very, very warm, okay? So this is a very, very exothermic reaction. So Mother Nature is going, this is a win-win, okay? I get to generate hydrogen gas, which later on we'll see increases the entropy. Entropy is a measure of disorder, and gases have a lot of disorder. And you're giving off heat. So what you'll see is that that's a win-win for Mother Nature. Mother Nature likes two things. It likes a big show, like a fireworks show, because it likes heat given off, and it likes a mess. Okay? So Mother Nature loves my room because I blow stuff up and it's always a mess. So Mother Nature feels very comfortable in this room because there's a large state of disorder. So that's the Chem 1 version of this. If you look at the net ionic equation of this, and this is what's actually going to give us more information, is if you cut through the chase and you get rid of those chloride ions, this actually tells us more information. So I've got solid magnesium, I've got aqueous hydronium ions, and now I have aqueous magnesium ions, and then I've got hydrogen gas. Okay? So I took a solid, reacted it with an ion, produced another ion that's now in the solution, and I produced hydrogen gas. So how could I tell that the magnesium, what could I look at to physically realize that the magnesium is turning into magnesium ions? What would I observe?
It appeared.
The
Yeah.
PPT disappear.
I'd watch the magnesium disappear, right? Like, well, I doubt I'm forming magnesium gas, okay? Right? It's possible, probably not likely, right? Because more likely I'm generating hydrogen gas. And I know if I generate hydrogen gas and I collect it and I put a flame up to it, whoop, make the test tube pop. So even though I can't see the hydrogen, I can test for it by collecting it. Okay, right. So now I've got a redox reaction taking place. So if you look at what happens on an atomic level, that magnesium has been together, those protons and electrons have been together a long time. Okay? Magnesium can only be produced in the death of the star. So this magnesium that I just used started at some point in the death of the star. So this is like stardust in effect. So the star blew apart. Okay? Somehow or another it ended up as part of this Earth when we were forming it. It then existed in a high enough concentration that we could mine it. We mined it, processed it, pressed it into a little bit of ribbon that ends up in the room of G20 at Mays High School. Okay? So this nucleus with those electrons, they've been together for a while. Okay? And now all of a sudden this proton comes along and says, hey, give us the electrons. Here you go. Okay? No loyalty whatsoever. Either that or maybe they're just tired of those electrons. Like, we have been together a long time. Go away. Okay? Go. Hang out with the protons. We're tired of you. Okay? Get away. So magnesium starts with an oxidation state of 0. It ends up at 2+. So some people like to look at this from a time, like a number line perspective. So the magnesium starts at 0. it ends up over there at 2 plus, okay? So it's going to lose electrons on the number line, it's going to move to the right. Well, if something's going to move to the right on the number line, what else has to happen?
Something has to move to the left.
Something has to move to the left. So, and again, this is just a visual way of looking at it. So the hydrogen sits here at 1 plus, it's going to end up at elemental. So if it gains an electron, it moves to the left. If it loses an electron, it moves to the right. Okay? And it doesn't make any difference where you start. If this had started off at Mg2 minus, and I ended up at elemental magnesium, it would go in this direction. If I start at elemental magnesium and it ends up at Mg2 plus, it's still going to move to the right. If this had started off at chlorine and it ended up at Cl1 minus, in other words, if I had elemental chlorine and it ended up at chloride, it would move to the left. Okay? Now, here's the other way that you can look at this, and we're going to spend a lot of time talking about this since that periodic table. So, on this reduction chart on the back, okay, and again, tomorrow we're going to spend a lot more time talking about this, I'm just laying this out for now. This is a reduction chart, okay, meaning that everything on here is being reduced. So if you look down here towards the bottom, where's magnesium? Down here towards the bottom, you have the reduction of magnesium, gaining 2 electrons and turning into magnesium. Now, we'll spend more time talking about the significance of this. But that has a negative E naught value. It's a measure of voltage. It's a measure of how willing it wants to go in this direction. If it has negative values, it really doesn't want to go in this direction. It actually wants to be reversed. If it has positive E naught values, it really wants to go in this direction. So basically what happens is this. The hydrogen, which is defined as 0, okay? So if you look right there in the middle, you have 2H plus 2 electrons yielding H2, and that's like our benchmark. That's defined as a value of 0. So we judge everything from there. So basically what happens is this. This magnesium gets reversed because it's oxidized. The hydrogen gets reduced and it goes forward in this direction. So whenever you have a redox reaction, you have one of these reactions that will go in this direction. You have another one that's going to get reversed. Okay? So this is why it's called a redox reaction. Something goes in the direction of this chart. Something else is going to go in the opposite direction of this chart. Okay? So one goes, one gets switched. So in this case, the magnesium gets switched because it's more stable going in the opposite direction. The hydrogen goes in this direction because that's easiest for Mother Nature. So if you reverse this situation, if you take hydrogen gas and try and react that with magnesium ions, nothing's going to happen. Because Mother Nature is going to go, no, we've been down this road. I ended up here, and I'm not going to reverse it. I'm not going to end up basically climbing out of the energy well. So this reaction puts us at the bottom of the energy well. So Mother Nature goes, oh, okay, I'm cool. Now, if you look at the second reaction that took place, we took hydrogen, it reacted it with oxygen in the air. Wow, this looks familiar. Kind of the problem off the test. Hydrogen and oxygen react together. You're going to get water. So to balance this, we go 2, boom, we're balanced, life is good. So, when you assign oxidation states, always start with oxygen. Oxygen is always going to be 2-. There is one exception and one exception only to that. That's if you have hydrogen peroxide and then oxygen is actually 1-. That's the only time oxygen is not 2-. Okay? So oxygen is always your kind of go-to anchor. Now, the other time oxygen obviously is 0 is if you have elemental oxygen. Then it has an oxidation state of 0. But if oxygen is bound to anything, oxygen is the one anchor that you can always count on. So, now, here's the other thing. Water molecules are neutral. So, if oxygen is 2-, what's the oxidation state of each of the hydrogens? 1+. Okay, and that's the other thing, we're going to do a whole worksheet on this in just a second, is being able to assign values to the oxidation states. Okay, so this is 1+, right? So what was oxygen over here? 0. Hydrogen was 0, oxygen was 0. So was the oxygen reduced or oxidized?
Oxidized.
So it gained electrons, so it's reduced.
Okay, so the oxygen went from being 0 to having 2 extra electrons.
Oxidized.
So it gained electrons, so the oxygen is
Reduced.
reduced. The hydrogen went from being 0 to 1 plus, so it lost electrons, so it was oxidized. Okay, now, so the irony is that the hydrogen was oxidized, okay? Sounds odd, but yeah. But now, this is where you get into reducing agents and oxidizing agents. So remember, the oxidizing agent contains what is reduced. So in this situation, what's the oxidizing agent?
The oxygen.
Oxygen.
The oxygen is the oxidizing agent. That's where that term comes from. Okay? And the hydrogen is the
Reducing agent.
reducing agent. Okay? So one of the most vital skills that you have to have is the ability to assign oxidation states to numbers. So you're not going to hand this in. I'm going to hand this out. We're going to go over it, but I want you to do a little bit of a practice with being able to assign oxidation states to these compounds, because you can't balance half reactions unless you know what the oxidation states are. So stop that for a second.
Do we get to do nitrates?